Welcome back, everybody. I hope everyone had a good weekend. So we're going to continue on with trigonometry. So we had talked about, in particular, that like sides and angles we mentioned will be used lowercase letters for sides, capital letters for angles, and we had talked about opposites. So to find out the opposite side, you just draw a straight line out from your angle. Whatever side you touch, that would be your opposite side. Right? And so with that, I want us to practice this because this is going to be very, very important in terms of the trigonometric ratios, which we'll talk about in just a moment. But so for angle A, wrong size font, for angle A, I'm going to draw this triangle just again, labeling it the exact same way, right? A in the bottom left, B in the top right, C at the right angle, and then A, B, C. So, in relation to angle A, lowercase a will be the opposite side. The hypotenuse is always the hypotenuse. Hypotenuse is always the side that is opposite the right angle, and consequently, it's always the longest side length. And that will not change regardless of whether you're looking at, like if you're focused on side or angle A or angle B. It does not matter. The hypotenuse is always the hypotenuse. But the opposite side to capital A, to the angle A, is lowercase a. And then the other side, B, is what we call the adjacent side. It is the adjacent side. So the adjacent side to angle A is lowercase b. Whereas for angle B, I don't think it's drawn the same, but doesn't matter. So now we're going to be looking at angle B. I'm drawing the B in pink. That's why I keep thinking about Barbie. That's my Barbie. Go Barbie. My son likes listening to that song. It's pretty cute. Oh, it was great. With regards to angle B, the opposite side is now the horizontal. This is now the opposite side. Whereas A is now the adjacent side. And the hypotenuse is still the hypotenuse. Once again, the reason why I'm spending so much time on this and discussing it is that when it comes to the trigonometric ratios, which angle you're starting with, which angle you're using, changes what is considered the adjacent and what is considered the opposite. So it is important to be able to identify it in relation to the angle in question. So example. For color. For angle A and B, angles A and B in the triangle below, identify their opposite and adjacent sides. So the triangle that's given, this one In the top left, you'll have A. Top right, you'll have C. Bottom right, you'll have B. And then so right angle at C. The horizontal distance, let me move this down a smidgen. The horizontal distance is going to be 24. The vertical distance is going to be 7, and the hypotenuse distance is going to be 25. So we want to find the opposite and adjacent sides for them. Let's start with angle A. So I'm going to use ADJ to mean opposite, adjacent, and OPP to mean opposite. Usually, in my experience, finding the opposite side is more natural, and then you can do the process of elimination to find the adjacent. As you do this longer and longer, as you do this more and more, you can kind of find it out immediately. But if you're struggling at first, find the opposite, and then the adjacent will be whatever's left. So the opposite side for A would be 7. And the hypotenuse is always the hypotenuse. It's never like the adjacent side is never the hypotenuse. So in terms of A, that was the opposite side, from C to B. The hypotenuse is from A to B, so this must be the adjacent side, the 24. For B, the adjacent and the opposite. So for angle B here, the opposite side would be shooting straight out, be 24. Is the opposite side, and the adjacent would then therefore have to be 7. Is that okay? Is there any questions on that?
So adjacent 7 or 7 is adjacent because
so 7 is adjacent. So for angle B, it's formed by these two angles. And yes, technically speaking, this the hypotenuse is adjacent to it, but I guess if we want in particular, when we say adjacent and opposite sides, we're talking about the legs of the triangle. So we're going to ignore the hypotenuse, even though the hypotenuse is technically adjacent to it as well. So it's the non-hypotenuse side that it's touching.
Okay.
That's another way to think about it. Yeah, so the adjacent side for B is the non-hypotenuse side, which would be 7 here.
Okay.
Mm-hmm. So why do we care? And that's because of the trigonometric ratios. A long time ago, mathematicians realized that there was a very, very useful significance to the ratios between right triangles. They noticed that there were certain connections between all of these things. And so they decided to call these ratios something. So definition, a trigonometric ratio is, of course, a ratio between any two sides of a right triangle. Trigonometric ratio is a ratio between any two sides of a right triangle. That's how they're defined in terms of right triangle. The first one, so we're going to be studying 3 of them in this course. There are technically 6, and I'll mention them briefly, but the 3 that we're going to be interested in is the sine of angle A or B, depending on the situation. And it's going to be, we write it sin parentheses A, and that's going to be the opposite over the hypotenuse. So sine, the way we say this is that sine of A. That's what that abbreviation represents. It says sine of the value A, sine of the angle A. So this is a sine, and this is a sine from above. The next one is called cosine of angle A or B. And the abbreviation for cosine is COS of A, and that's just cos. Thank you. Appreciate it. There's a lot of jokes with trig, by the way. There's a lot of jokes with trig. And that's going to be adjacent over hypotenuse. And the last one, the last main trig ratio, is the tangent of angle A or B, depending on the situation, is tan of A, and it's going to be opposite over adjacent. So I hope you understand now why I was spending a little bit of time making sure we understood to identify opposite and adjacent sides of an angle, because it matters which angle is in question. So warning. Since the opposite and adjacent sides are dependent upon the angle we're using, we always specify the angle. Because sine of A is not necessarily equal to sine of B. There's only one situation where that will be true. Cosine of A does not always equal cosine of B. Very rarely. In fact, only once does it work that way. So we will always what I mean here is that, let's say you get your answer and you're going to say that it's going to be sine is equal to 4/5. This is not mathematically correct. To say sine or sin, like sin is the abbreviation. To say this is nonsense in mathematics. You'd have to say sine of A or sine of B or whatever. Sine is kind of like, imagine like the square root symbol, right? It gets operated on a number. Same thing's true with sine, cosine, and tangent. It gets operated on a number. So you write sine of a number, and then you can compute it. So those are the three main trig ratios. Now, they're ratios, so you could also just flop them, right? You could flip them on their heads. You could also talk about hypotenuse over opposite, or hypotenuse over adjacent, or adjacent over opposite, right? Those are the three other trig ratios that we're not going to talk about. They're more useful in Math 127 and so on and so forth. But in case you're curious, they are hypotenuse over opposite is cosecant. Hypotenuse over adjacent is secant, and adjacent over opposite is cotangent. So either way, how do we remember which one's which? The remembering tool that every kid is told. Yes, indeed. SOHCAHTOA. Imagine that's what Squidward says when he's the superhero with the volcano on his head instead of Krakatoa. He's SOHCAHTOA. Yes. So what it represents, so sine is opposite over hypotenuse, right? Sine of blah is equal to opposite over hypotenuse. Cosine of whatever is adjacent over hypotenuse, and then tangent of the angle is equal to opposite over adjacent. They can't all be, please excuse my dear Aunt Sally, like PEMDAS, right? We don't get all the nice ones. I don't know how this is a remembering tool. It's just what was beaten to our heads. Teacher just busted out the ruler. Kidding, of course. But I do remember being constantly bopped on the nose to remember this one. The SOHCAHTOA. So remember it somehow, it's SOHCAHTOA. That's the best I got for you. I don't think anybody's found of it. Like, if anybody knows of a different way to memorize it, please let me know. The SOHCAHTOA seems to be the best way. So Katoa. You might be asking yourself, why? What's the point? Why do we care about this? And that is a good question. And so we're going to do a simple, like we're going to do a basic example of finding the different trig ratios. And then I'm going to explain why it can be useful. So, example. Find sine, cosine, and tangent for angles A and B and reduce your fractions as much as possible. So the triangle in question, this one. So A is in the top left, B is in the bottom right, C is the right angle. And then it says the vertical is 21 meters. The horizontal, the base, is 72 meters. And the hypotenuse is 75 meters. So with this one, you can, so we're gonna have to find sine, cosine, and tangent for A and for B. What you could do is like, if you're gonna have to find them anyways, you could just find out what the adjacent and the opposite sides are for angle A and then find them all. But I think that's actually gonna do you a disservice instead of being able to look at the triangle right off the bat and figuring out which one's which. That being said, you can totally do that. You can totally list them out if you want. But for angle A, the sine of A. And so looking at A here, the opposite side is what? 72, and the hypotenuse is 75. So opposite of our hypotenuse, so 72 divided by 75. Now there's a common factor of 3 between the two of them. 72 is 3 times 24. And 75 is 3 times 25. So the common factor of 3 will cancel. And you get that this reduces down to 24 over 25. Another way to do the exact same thing is to divide the numerator and the denominator by 3. You do that too. Or if you have a calculator, it will usually reduce it for you. If you have one of the calculators that I recommended, it will reduce it for you. Other scientific calculators can reduce the fraction for you, but you have to do some tricky things. And if you let me know, if you don't have the calculator I recommended, I can tell you how to do it. Yes.
Where did the 24 and 25 come from?
So I knew what the factorization of 72 and 75 were. I knew that they had a common factor of 3. That's the only reason why. But you could just as easily, I've seen students do this. So you got that 72 over 75. I've seen students divide the numerator and the denominator by 3, and that will reduce it down to the 24 over 25. Either way is fine. But a little thought bubble. Side note land. Okay. Sine of A is done. Cosine of A is going to be adjacent over hypotenuse. This is the opposite side for A. This is the hypotenuse. This must be the adjacent. So it's going to be adjacent over hypotenuse. So 21 over 75. And by a similar argument, they both have a common factor of 3. 21 and 75 are both divisible by 3. So this reduces down to 7 over 25. And then tangent of A is going to be opposite over adjacent. So 72 over 21, which all three numbers are divisible by 3. So if you divide the numerator and denominator by 3, you get 24 over 7. So please, I definitely know. I know you're probably wondering, like, why is this a thing? Mathematicians are just being mean. Like, is that the only reason why they just want us to do something else? Just that's probably it. That's probably the real reason why. Mathematicians are kind of jerks. It's true. Just weirdos. No, it's 100% true. It's 100%. Most mathematicians are weirdos. We all some of us own it better than others.
Is it like the Dungeons and Dragons kind of weirdos? Like, no, but
No, not taken. Dungeons and Dragons is awesome.
I want to try.
It's actually pretty fun. Need a good group of people for it though. But just all over the spectrum, all spectrums of weird. You'll find mathematicians everywhere.
That's fair.
There's ones who are really, really interested in sports and fantasy football, that type of thing. They're just the same.
Yeah.
Just fantasy football is it's Dungeons and Dragons for football. So
I have my good
okay, Siri, I'll explore the facts. No. I think I keep accidentally hitting the little button on the side when I bend my wrist or whatever. But anyways, there is a reason to it. There is a justification, and I'm gonna finish this problem. We're gonna do another problem right afterwards, and I'm gonna explain to you why it's useful. So for B, I'd like you guys to all do B. For angle B, just do sine of B, cosine of B, and tangent of B. And I'll bring the triangle down so you've got it for reference here. Highlight that we're using angle B here. And the answers up here, if you'd like to check your work, if you're still working on it, continue to do so. Have you noticed any similarities between the angles A, like the trig ratios for A and the trig ratios of B? Notice that the sine of A is equal to the cosine of B. And cosine of A is equal to sine of B. That's actually the reason why it's called cosine, right? Like knowing our little Latin roots and stuff, like when you hear people say co-founder or co-producer or whatever, people working in tandem together. Cosine, it is closely related to sine. They are paired together. That's the reason why it's called cosine. I don't know why sine is called sine. Just because, I guess. I'd have to look into, like, I should probably figure out the reasoning for it. I'll look into it at some point in my myriad of hours of free time, right? We all have. So, but that's the reason why it's called cosine, is because it is what we call it a co-function. But that's besides the point. So that's how you find the trigonometric ratios. Now, the reason for it, this is in the other example, and then we'll explain why we're studying it. Example. Unless there's any questions on that problem. So compute with a calculator and round to 4 decimal places. Part A is going to be sine of 38 degrees. B is going to be cosine of 33 degrees. And C, tangent of, someone give me a number, prime number. What? 27 is the prime? Is it prime?
Is 7 a prime number?
7 is a prime number.
Say 7.
27 is divisible by 3, right?
If we composite, it's a prime, there's only-
So 29 is the prime number. 29 is the prime number, right? Is this important? No. But let's do tangent of 29 degrees. So if you have purchased a scientific calculator, now granted, the calculator on Canvas will work as well, but one thing that's important is your calculator has 2 different modes of angle measurements. There's something called degrees, which is what we're going to be what we're mostly used to in our real world, and then there's a thing called radians. We are not going to be using radians for this course. If you'd like to know more about what a radian is and how to use it, please feel free to talk to me. I will bore you to tears. But we're going to be using degrees. Now, the most scientific calculators will come standard in degrees, I think, but you should be able to see at the very top of your calculator a D or an R highlighted. If it says D, it's in degrees and you're all good to go. If it says R, then you're going to need to change something. For this calculator and for the one that's similar to it, you have to press Shift and then go to Setup, and then it'll give you an option to change the angle unit. And so you press 2, and then you'll change it to degrees. You're not going to need to switch it to radians at all. We're going to keep things in degrees in this course. So, also, if you have a scientific calculator, there should be a sine, cosine, and tangent button. Oops. Great thing about these things is they are very, very resilient. So sine, you press the sine button and then do 38 degrees. You should get 0.615661 on and on forever. Because sine of 38 degrees is going to be an irrational number, meaning it's a non-terminating, non-repeating decimal expansion. It'll go on and on and on forever. So I'm just writing it down several digits, and we're around 4 decimal places. So 6156. Looking to the number to the right, it's greater than 5, so we'll round up to 0.6157. cosine of 33 degrees, cosine of 33. You get 0.8386705 ... which approximates to, I wrote 888 and I meant to write 838. So 0.8386705 ... rounding to the nearest, so tenths, hundredths, thousands, 10,000s. So 4 decimal places, rounding to the nearest 10,000 would be rounding up. So 0.8387. And then tangent of 29 degrees is 0.554309 ... on and on forever. So rounding to the nearest 4th decimal place. Looking to the right, 0, so that's less than 5. So we'll round down to 0.5543. So back in my day, not really, because scientific calculators were still were pretty impressive back in my day. But before my day, back in my mom's day, we didn't have a calculator that can compute sine of 38 degrees. It had to, we had to have an appendix at the back of our textbooks that had sine of 1 degree, sine of 2 degrees, sine of 3 degrees, sine of 4 degrees. And like my mom has showed me one of her textbooks that has that. It's like this old textbook, and it just has all of them. But now we have it at the palm of our hands, right? So every degree measurement, the ratio is the same, no matter what happens. The thing is, the sine, like sine 38 degrees is always that specific number. So if you draw any triangle, like, and you draw a 38 degree like, let's just assume for the sake of an argument that this is 38 degrees, right? No matter what happens, no matter what the side ratios are, that's still a 38 degree angle in the bottom left. And the sine of that number is still going to be 0.6 or whatever it is, no matter what size of triangle. If you do the ratio between the two side lengths, it will always boil down to 0.61 or whatever it is, 0.6157, which is pretty cool. That's how the Greek mathematicians recognized it. They were like, wait a second. If I make this a 45 degree angle and I make this a bigger triangle, it still ends up having the same ratio. It's still like the ratio still boils down to the exact same number. That's impressive. That's strange. And so from there, all of trigonometry was formed, and people have hated us ever since, right? But the point being is now, if we don't have a side length, but we know the angle, we can find it. So that's what we're going to do in this example here. Find the measure of side B. Find the measure of side B. The triangle that's given is this one. Bottom left is B, top right is A, right angle is C. And then angle B is a 32 degree angle. And then it lists B is unknown. The hypotenuse C is unknown, but the base length is 22. So now, if we had side C, right? If we had side C, we could use the we could use the Pythagorean theorem that we learned, right? Because a squared plus b squared is equal to c squared. But as it stands, if we were to try and use the Pythagorean theorem, we get 22 squared plus b squared is equal to c squared. That's two variables in that equation, and we can't solve for one or the other. So that's why this is where trigonometry comes into play. So for angle B, solution, for angle B, the opposite side, what is the opposite side? Lowercase b, the adjacent, close, 22. And the hypotenuse is C. That's right. So, TOA, which trig ratio would be useful here? Exactly right. TOA, tangent. Because and it's okay if you don't realize it off the bat, right? You have 3 different ones that you can use. If you don't get it right first, you got 2 other ones that you can try, right? So TOA, third time is the charm. Exactly right. So if you wanted to try, oh, no, not that. If you wanted to try and use cosine, adjacent over hypotenuse, we don't want measurement C. So TOA, CAH, cosine is all out. Sine, opposite, we want to have B, but hypotenuse is C. And that would allow us, that would have 2 variables in the same equation. It would not work for us. So is out. So it must be that we're going to be using tangent. So tangent of B is going to be opposite, which is lowercase b, over adjacent, which is 22. And so that's going to be tangent of 32 degrees is equal to b over 22. Now, this looks intimidating at first, because we've never really seen a trigonometric like trig being involved in equation before. But the thing you have to remember is that tangent of 32 degrees is a number. The trigonometric ratios, they take in an angle and spit out a number. So while we have it written as this tangent of 32 degrees, it is a number once we plug it into our calculator. Just like if you were to plug in square root of 10, we don't know what it is right off the bat, but when you plug it into your calculator, you get something like 3.2-ish or 3.1-ish or something like that. So what we do is we use our calculator, because there's no way to do this otherwise. Like I do, like you could come up to me one day in in Albertsons parking lot someday and say, "Hey, Phil, what is tangent of 32 degrees?" I would not be able to tell you. I don't know what it is off the top of my head. So that's why we need a calculator here. So tangent 32 degrees is 0.624869 on and on forever. When it comes to this stuff, I recommend probably writing down 6 decimal places. That should be sufficient, because this thing will go on and on and on forever. You can write down all the decimals on your calculator if you really want to, but you probably will get the right answer if you write down 5 or 6 decimals. So let's just stop it there. No. Let's just write down 5 decimals. That should be sufficient. So 0.62486 or 87, because it's 6.9, so round up, is equal to b over 22. There are 2 ways to solve this. One way would be to multiply both sides by 22 to kind of undo the division by 22. That would be the way that I would want to go. However, that only works if your variable is in the numerator, but sometimes your variable will be in the denominator or the bottom. So it's best to use cross multiplication for us. So we're going to think of our decimal as a fraction by putting it over 1 so that we can cross multiply. And we'll get that b is equal to 22 times 0.62487, which is 13.74714. And it didn't ask us to round. We're just like, whenever that happens for the remainder of our course, if it doesn't specify to round, we'll just round to 2 decimal places. How about that? So this will be approximately 13.75. And no units were given, so we can just box it in like that. So, despite not knowing what the hypotenuse was, we were able to find B without using the Pythagorean theorem. We were able to use the sine, cosine, and tangent to our advantage. That's one of the first ways that we can use sines and cosines and tangents. You can really use triangles everywhere in life. Not everywhere in life, I guess. But you can always inscribe triangles into things. And that can be very, very useful. So we're going to do an example in just a moment to show you that is the main thing that we're going to be using it for, is to solve for missing side lengths. But there are so many implications that trigonometry has given us in the world. Just in case you're curious and want to know more about it, there's a very famous mathematician. You don't need to write this down, but Fourier. I know it looks like Fourier. But he was French. He found out that you can take any curve in space, any curve that you define, like draw any curve you draw, you can actually represent it as a sum of infinite. So like this isn't going to make very much sense. Sine of n pi x over L plus b sub m times cosine of m pi x over L, which looks absolutely crazy, right? What this is saying is that you can write any curve that you draw in space as an infinite sum of sines and cosines, which is miraculous and might seem really stupid at first. Absolutely, I completely agree. When you look at this at face value, you're like, that seems like making it way more complicated. But when it comes to very, very complicated curves, breaking it down into sines and cosines makes it actually very, very easy to work with. So that was a very, very fascinating discovery that gets, you can even see visualizations of Fourier series. Like people have used Fourier series to draw pictures of like actual portraits of Fourier, the mathematician who found it out. Yes.
Have you used SOHCAHTOA in your lifetime?
So I use it all the time in mathematics. And therefore and physicists will use it. And basically any engineer who has to deal with angle measurements at all, so civil engineers especially, will probably use sines and cosines, and SOHCAHTOA. Like SOHCAHTOA is the basics of it. They start using it for more and more complicated things. But civil engineers 100% will use angles all the time and therefore use the trigonometric ratios. But for us, for the average person who doesn't really want to study mathematics in detail, though everyone should, right? Because it's a super fun thing to do.
I could never be a mathematician.
No, I get you.
What major I'd be switching right after the class.
I understand why some people don't like it. I think it's fascinating. And
I think it's train our brain.
it's a very, very good like it really stretches your deductive reasoning, and that's honestly one of my favorite things about trigonometry in particular. If you ever decide to take it, I think I've already mentioned this before, but really recommend taking my wife for Math 127 if you ever decide to do it. She does a really good job, and because the way she approaches it and the way that I do, but she does a better job at doing it, is as little memorization as possible. Little memorization in mathematics as possible, because all you need to know for trigonometry to basically succeed in it, as long as you're willing to put in the work, is you need to know the trig ratios. That's 6 things you need to memorize, plus sine squared plus cosine squared is equal to 1. Everything else can basically be deduced from that, which is crazy. So it's a very fun course. I love teaching it, but I usually let my wife take all the courses sections of it if she wants to, because she likes teaching it way more than I do. Not saying that I don't like trig. It's just I like to make her happy, and if she's gonna get to teach Math 127, she's happy. Anyways. Example. Point being is that there are many implications to what trig can do for us. We're going to be using it for the solving of sides and things like that, but there are other things that it can do. So example, a plane takes off at a 14-degree angle. After flying straight for 15,000 feet, what is the altitude of the plane? Round to the nearest whole number. Round to whole number. So I am a person who needs to have a picture. Like if you're built different, like you can crush an egg with your hand, you know, that type of thing. If you've never tried to do it, it's actually very, very challenging to crack an egg in your hand, like squish an egg. Try it next time. Just grab an egg from your kitchen and try and squeeze it with your hand to crack it. It's very, very difficult to do. I'm not trying to troll you or anything like that. I didn't believe it when I saw it, but try and crack an egg with your hand. Try and just crush an egg with your hand. It is very difficult. Say what? Sadly, I have to obey the syllabus, and the syllabus says that there's no extra credit. So sadly, no.
What if it's
Two in one hand? Actually, that would make it easier. Cracking 2 eggs in one hand because you have a pressure point that you can use.
I didn't think of that.
So if you can do this without visualizing it, that's great. But I recommend drawing a picture, especially. I took this one straight from our from one of our homework exercises or something like that because I was a little upset about the wording and I wanted to clarify. So when I read this first, after flying straight for 15,000 feet, I thought it meant after flying this way for 50,000 feet. What it's talking about is while going at that 14-degree angle, you're flying on that at that 14-degree angle for 15,000 feet. So what the picture will look like is here we have our runway. Runway. We have our little plane. So very, very important. That's a pretty accurate plane, I gotta say. I'm pretty good at drawing planes. Fine, I'll add more depth if you're gonna sass me.
Like I think it's actually really good for a quick drawing.
Well, thank you. I appreciate it. I'm self-conscious, okay, guys. And so it's flying up on color at a 14-degree angle from the ground. I don't know why I made it dashed. I just because. And so this measurement here, this is 15,000 feet. Was I the only one who was kind of confused about like would have assumed that they meant the bottom distance?
Mhm.
So just so we're clear, like just if this happens again, that's what they mean by flying straight at that 14-degree angle. So that's 15,000. We want to know the altitude, which would be the height right here. That's the altitude. We call it X, we can call it H, call it a doggy face, whatever you want to do. Whatever you want to do, as long as it's a variable. And then we're not really interested in the base measurement. We could find it, but we're only really interested in the altitude. So in comparison to the angle, the 14-degree angle, what sides do we have? the opposite side, and we have the hypotenuse. So, which one? Yes, the hypotenuse is 15,000. So looking at SOHCAHTOA, which trig ratio should we use? Cosine would be adjacent over hypotenuse. So, yeah, so we're gonna use sine. Now, granted, one of the great things about trigonometry, in my opinion, is as long as you have two angles and one side, or one side and two angles, you can find everything else. So you could use cosine, and that would get you this measurement. Then you have this measurement, you have the hypotenuse, you can solve for the missing leg by using Pythagorean theorem. So there's many different ways you can go about solving them, but the fastest way would be using sine. Because you have the, you want the opposite, you have the hypotenuse, and you have your angle. So we have sine of 14 degrees is equal to the opposite, which is x, over the hypotenuse, which is 15,000. Now, using your calculator, because I don't know what sine of 14 degrees is off the top of my head, it's going to be 0.24192. So 0.24192 is enough digits. I think that should be sufficient. If you want to write more, go ahead and write more. You'll get a more accurate measurement, but this should be sufficient. 5 decimal places is usually enough. Which is why I never really understood sig figs. Legitimately, why not just write as many as you can? So significant figures or significant digits, I've always disagreed with the concept, but I'm not a chemistry person or a physics person. So 15,000, and then we're gonna imagine that our fraction is our decimal number is a fraction by putting it over 1 to cross multiply. And we will get that x is equal to, so 15,000 times 0.24192, you get 3,628.8. So approximately, if we round up to 3,679, 3,629 feet. So the plane is 3,629 feet above the surface. Now, granted, yes, the Earth is a circle, it is a sphere, yes. So technically, ground isn't perfectly flat, but the Earth is so large that it's essentially flat in that small of a span. And it's supposed to be a rough estimate rather than anything else. When I originally, my previous class, I actually did this. I had used the measurement of miles. So it travels 15,000 miles, and then you'd be 3,629 miles above Earth, which is in space. Because apparently the stratosphere is only about like 30,000 feet up or something like that. I can't remember what. So like 3,000 miles would be way out in space. So I fixed the measurement this time. But that's that. Are there any questions on that one? How to do it. Okay. There's one last little topic before we can actually do our last examples, and that is a nuanced situation that you'll hear in problems, which is the concept of the angle of elevation slash or the angle of depression, which I'm going to now abbreviate to be AOE or AOD. It's not depression the way we would think about it, like mental health wise. It's the literal definition of what depression means. So like, if you're like lower than you, yeah. So not I mean, granted, if you're depressed, you're probably looking down. So it works out in that aspect, but more importantly, we should not be joking about, that's not a joking matter. The serious thing. But how do we define it? Because you'll see it in problems, let's say the angle of depression is this. What is the angle of depression? So I've got a picture to kind of showcase it for you guys. So for the angle of elevation, the AOE, area of effect, right? Observer. So in these problems, there's usually a person or a thing that is observing the angle in question. And so from them, you have their horizontal. So if the observer is looking directly straight, that is their line. And then the object is above them. So the object being observed. Up here, the object being observed, like this, the angle that is formed here. This angle is the angle of elevation. That is the angle of elevation. So when you're looking straight, the object of that you're looking at, that measurement, that angle is the angle of elevation. Whereas the angle of depression, as you might imagine, is done similarly. Observer, it's right here. And then you have their horizontal, the way they would view the world by looking completely straight. And then you have the object that they are observing, which is below them. And so this one would be down. So the observer is going to look down to the object, and that angle is the one that is the angle of depression. That is the AOD. And so, like, we just have to have this little bit of information because otherwise it doesn't make sense when you're reading the problems that involve the angle of elevation or angle of depression. So I want to do an example of that. So, example. A security light is going to be mounted to a building. So that the AO, is everyone okay with AOD for the angle of depression? Like, so I don't have to write angle of depression. It takes so long. It's very warm in this room, and I don't want to write. A security light is going to be mounted to a building so that the angle of depression for the beam of light is 30 degrees. How high up must the light be posted? Must the light be mounted so that it will shine on a spot that is 20 feet from the base of the building? Terrible. Realize it's going to be mounted to a building so that the angle of depression being of light is 30 degrees. How high up must the light be mounted so that it will shine on a spot that is 20 feet from the base of the building? So let's draw a picture to better view this. Once everyone's finished writing, I'm going to take a second. I know I write very quickly. We'll draw a cool little building. Little windows. Revolving door. And then so the little security light is going to be right here. And it's going to be shining a light down. Onto the floor. That is that. And so it says that to be on a spot that is 20 feet from the base of the building. So not the length of the diagonal, but the length of the base is 20 feet. And we want to know how high up to put this light. So we're asking for the vertical distance X. So this distance right here is X. Says the angle of depression, though. So whenever you see that, you should always draw kind of a medial line stemming out from the object's field of view. So we're going to draw a little line out. And so this measurement right here, this measurement is 30 degrees. Not the angle measurement below, but that angle measurement is 30 degrees. I'm realizing people watching the recording, not this angle measurement is not 30 degrees. This is 30 degrees. So John Doe's student says, oh, well, I've got the opposite side, I got the adjacent side, so I should use tangent of 30 degrees equal to 20 over x. But that doesn't work because that's not part of the right triangle. So this, if we wanted to use 20 over x, we'd need to know what this angle is. So there's two ways we can go about doing this problem. So option one, to find red angle and use it. Option two is to be clever. But now, once we learn the way, this clever way, we're all going to realize this. Whenever you draw a triangle, you can inscribe the same triangle above it to form a rectangle. So what I mean by that is we can create this triangle here. This triangle here is the exact same triangle, just flipped. So this vertical distance in purple is the same as the pink. Does that make sense? So this is X, and this this lavender one, this lavender dotted line is 20 feet as well. So you can do it that way. And that would be the faster way, in my opinion. So let's do it the clever way here. So now we can use our 30-degree angle. We've got our opposites. So we want to know our opposite side, and we have our adjacent side. So we're going to use tangent, SOHCAHTOA. So tangent of 30 degrees is equal to x over 20. Tangent of 30 degrees is 0.577. 0.35 and then a 0. So that I think that'll be a good enough approximation, is equal to x over 20. And then we'll treat our decimal number as a fraction by putting it over 1. And then we can solve this by cross multiplication. And you get that x is equal to, so 0.57735 times 20 is 11.547, or approximately 11.55 feet. It didn't say to round, but I'm going to round to the nearest 2 decimal places. I think that'll be good enough. But what if we weren't clever? Unless there's any questions on this whole process here. So whenever you draw a triangle, you can always flip the triangle over to create a rectangle that has the exact same measurements, just in slightly different orientations. Does that make sense? Now, if you weren't clever and didn't realize that, how would you solve this one? Because the red angle is not 30 degrees. Does anyone know what it is? No, sorry, what is the measurement of this angle here? Realize it is 60 degrees. And that's because we have formed a 90-degree angle here. So this, the measurement of this angle is 90 degrees minus the 30 degrees from the original angle, and you get 60 degrees. So then we have tangent of 60 degrees is equal to 20 over x. And we can solve it like normal. I get like just in the interest of. No, I think we're okay. No, we should call here. But you can solve this one that way as well. It's going to be the exact same thing. Find the value of that thing, write down about 5 decimal places, cross multiply, and you'll need to do one extra step. You'll need to divide. But well, we got time. So tangent of 60 degrees is going to be 1.73205 is equal to 20 over x. We'll treat it as a fraction and cross multiply. So we get 1.73205x is equal to 20 times 1, or just 20. So this is the extra step that we have to do. So we had to do 2 extra steps. First off, we had to find what the red angle was. Then, instead of just having x here, now we have 1.73205x is equal to 20. Yes?
Instead of option 1 where it's 20 over x.
So remember, it depends upon the angle that's being used, right? So with the triangle formed with the 30-degree angle, the opposite side, so tangent is opposite over adjacent, whereas with the red angle, the opposite side is 20 and the adjacent side is x. So it depends on which angle. Like, does that make sense? So to reiterate, the angle will show which angle you're using will change which side is opposite and which side is adjacent. So the reason why it is 20 over x versus x over 20 is that the angle is different. Yeah, the angle is different, making the adjacent and opposite sides different. And so to solve for x here, nothing too crazy. We're just going to have to undo that multiplication by 1.73205. So we'll divide by that number. And I know it's a nasty looking number, right? But we still got to deal with them in real life, right? We got to deal with nasty numbers every once in a while. We don't like to work with the closing shift who always just talks and doesn't actually clean. That's never a fun person to work with, right? Well, they're fun because you can talk with them, but then you get out at midnight instead of being out at 10 with the other shift supervisors. Not talking about from personal experience. But if you do this, so 20 divided by 1.73205, you get 11.5 547 dot 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 dot. So 11.55 feet as well. You didn't get the exact same number because we used a different approximation, but it was close enough for what we needed for the answer. Any questions on that? Okay, so we'll start off section 1.5, which is circles and composite figures. Circles and composite figures. So we're going to first talk about circles, and then we're going to talk about composite figures afterwards. We're not going to get too far into this, but we'll get the first, at least the definitions. So circle definitions. And to maybe have a little bit of fun with the definitions, we're going to draw them visually. So I want you to draw 3 different circles. And if possible, try and draw them all to be the same. I am just that good. I can actually draw them to be perfectly the same. See, look at that. I just drew the perfect circle.
3 times. That's great.
Yeah, I not only can I do it twice, I can do it 3 times all the same. And so the circle is comprised of that thing, and then there's always a center to the circle. So just draw the center in all of them. And for all of them, I want you to draw a line through the center from one side to the other. And I'm going to do different types of highlighting for them. So for the first one, the distance all the way around the circle, this distance right here. That is called the circumference. And that is the perimeter of the circle. The circumference. It's also one of the Knights of the Round Table, circumference. But technically speaking, perimeter has to deal with the sides of a shape, and a circle doesn't really have sides. It has one side. It is a continuous line. So it doesn't really have sides, but the idea is still the same. The circumference is the distance around the circle. It's like the perimeter is the distance around the sides of a shape. So circumference is the perimeter. Then if you were to highlight the entire line that goes from one side of the circle through the center to the other side, that is called the diameter. It is the distance across the circle. But if you were to shorten that to just go from, instead of from one side of the circle to the other, rather the center of the circle to the outside, that is one of the ones we know and love, which is going to be called the radius. Which is the distance from the center to any point on the circle. Let's see, we got 1 minute. We'll call it good. We're going to talk about the connection between the diameter and the radius next time. If you don't and if you already know these things, great. If you don't, great. We're going to talk about them now. Well, not now. on Wednesday. Okay, guys? If you have any questions, feel free to email me. Otherwise, I will see you guys on Wednesday. Sorry, like I can't remember if it was a couple students from this class or the other class that emailed me. If you send me an email and I haven't responded, I'm going to get to it. I did not get to campus as early as I wanted to. Don't blame me, blame my son. It's not my fault that he wanted to go play with his cars. And I could not leave that situation. So anyways, if you guys have any questions, feel free to email me. Otherwise, I'll see you guys on Wednesday. Have a great rest of your day. Okay.